Okay,
Okay,
guys, so
let's
what are
go.
we finally doing? It's been 3 hours and we still have no topic.
Um, I don't know, man. There's not a lot of scope at home. I can't think of anything. Mm,
How about if we do it on microwaves?
I think someone's doing microwaves.
Hmm. Yeah.
What
Anyone
about
else?
what about the physics of walking?
I mean, he used it as an example to explain what the exhibition is about. So, like,
Oh
I
yeah.
mean, I don't think we should take that.
So
Guys, come on. It's like time for me to eat my lunch.
Yeah,
Oh,
same.
wait a second. I know what we can do. Quartz
what?
clock.
What?
Quartz clock. So basically, have you ever wondered how a clock works? Like usually in physics, we only study like pendulum clocks or digital clocks. What about a quartz clock?
That sounds like an interesting idea. Let's get into it.
Okay, sure.
A basic analog quartz watch has 7 parts connected in a circuit: a battery, a stepping motor, a microchip, a quartz crystal oscillator, a crown screw for setting time, gears to turn the hands of the watch, and a central shaft. Before we talk about how exactly the watch works, we shall talk about piezoelectricity, the principle behind the quartz watch's functioning. Piezoelectric effect is the ability of certain materials to generate an electric charge in response to applied mechanical stress. The key thing to remember about quartz is that it's piezoelectric. It will vibrate when you put electricity into it, or it will give out electricity when you vibrate it. A quartz crystal oscillator uses piezoelectricity in both ways at the same time. The battery supplies a current to the microchip circuit, which is designed to make the quartz crystal vibrate. The quartz crystal itself is very small and is precisely cut and shaped like a tuning fork. When a quartz crystal is properly cut and mounted, it can be made to distort in an electric field by applying a voltage to an electrode near or on the crystal. This property is known as electrostiction or inverse piezoelectricity. When the field is removed, the quartz generates an electric field as it returns to its previous shape, and this can generate a voltage. The result is that a quartz crystal behaves like an RLC circuit composed of an inductor, capacitor, and resistor with a precise resonant frequency. This frequency is usually 32768 Hz. This is just high enough to exceed the human hearing range, yet low enough to permit inexpensive encounters to derive a 1-second pulse. The basic formula for calculating the fundamental frequency f of vibration of the quartz cantilever as a function of its dimensions is: in this formula, L is the length of the cantilever, A is its thickness along the direction of motion, E is its Young modulus, and rho is its density. The microchip takes this voltage as binary input, and a 15-bit binary digital counter driven by the frequency will overflow once per second, creating a digital pulse once per second. This output powers the stepper motor, which turns the gear system. The gear ratios are shown here. The question arises that if the quartz watch is so precise and efficient, how does it lose and gain time? This is because piezoelectric properties are temperature and pressure sensitive, hence keep fluctuating minutely. Standard quality 32768 Hz resonators of this type are warranted to have a long-term accuracy of about 6 parts per million at 31 degrees Celsius. That is, a typical quartz clock or wristwatch will gain or lose 15 seconds per 30 days with a normal temperature range of 5 to 35 degrees Celsius or less than half a second clock drift per day when worn near the body. Most manufacturers just program the microchip to skip a small number of crystal cycles at regular intervals, such as 10 seconds or 1 minute.
Yeah, so that's basically how a quartz clock works. What do you guys think about it?
Jonathan, I didn't get any of that. Did the audio break for any of you?
Yeah,
Yeah, I think your mic was off.
Oh man.
Yeah. Can you just say all of that again?
No way. Goodbye.